And we are live. So I'll just quickly check that things are working fine. Live. Okay, so let's get started with day 4 of Advent of Code. And we have been doing this for the last 3 days now, and like for all the 3 days we were able to solve both the parts live. Let's see like how long this streak continues for, and this is the 4th day. So let's get started. uh, yeah, if I am able to solve this quickly today, then we can definitely go ahead and solve this in Rust. uh, so every day, like, it takes up some time to solve this, so I avoid solving it in Rust. But I'll soon publish these videos on my YouTube channel where you can go ahead and watch the solutions in Rust. uh, Go mod init AOC day 4. Again, we will do the same stuff first. Like, have a main.go file. So we have this main function. Okay. Yeah, we'll create this input.txt file for any input, and I'll just also copy this input. So let's read the puzzle first. So we have this grid. uh, I don't know the length, like the maximum length that we can have, but let's so in this example there are 13 rows rolls of paper that can be accessed by forklift. So how can we access this roll? So we have this grid where we have like some empty positions which are marked by this dot, and we have this paper rolls that are marked by at the rate character. And yeah, and what we have to do is that we can have a forklift that will access the rolls of paper, and we want to mark that which rolls can be accessed. And if there are fewer than 4 rolls in the 8 adjacent positions, so we just have to check for all the 8 adjacent positions, like 3 to the top, 3 bottom, and 2 on the side. So like all these 8 positions must be checked, and if there are fewer than 4 rolls, then obviously we can pick that up, or we can access that. For example, this paper, so we have like 1 uh, and 2, so we have only 2 rolls here, so this can be accessed. But similarly, this paper, can we access this one? So we can access this one too, which is okay. Let's try to see that if we can access this paper. So 1, 2, 3, 4. So there are 4 rows adjacent to this one, therefore it cannot be accessed, because we should have less than 4 rows on all the sides. So just to quickly go over the diagram, we have this paper here that is in consideration, and we have 1, 2, 3, 4, 5, 6, 7, and 8. So out of all these 8, if there are, again, if there are papers, like if there are 4 less than 4 rows on the adjacent side, then we can access this paper. Similarly, like if it is true for this paper that is under consideration, it is also true for this paper under consideration. So again, for this, again we will have these 6 positions, sorry, these 5 positions, and the third and the 3 positions adjacent to it. Then we can see if we can access this paper or not. So similarly, so what we need to do is we just have to iterate over all the paper rolls that we have, and we need to check all the 8 positions. And if there are less than 4 papers on, like, surrounding that piece of roll, then we can access that using forklift. And we just need to count how many of them are there. So it's not a very tough problem, seems pretty easy. We just need to read the input properly. So let's get started with that. So I've just pasted the input here. Again, yeah, like today we will try to read the input in the best possible way. Let's try os.open file. Name flag permission, and name is obviously input.text. Most users will open or create instead. It opens the file with specified flag. Uh, let's just give this flag value as 1. Os dot I don't know what is this flag. So what we can go do is that we can just query Claude for a solution here. Yeah, this is a whole new chart. What is the right way to read file in Golang which is also optimized using buff IO? So till now we have been using, like we have been reading the entire content, which is not the right way. So for example, if we have a very large file, like reading the whole file and putting it in memory is not the best practice. I think buff IO is buffered input output, which is like much better as compared to using io.readall. io.readall works for our purpose, but it shouldn't be the thing that we should like follow. Okay, so we can use os.open. I think this is much easier. os.open better than os.open file. So os.open. I think this should be okay, and it gives us the file and the error. If error is not nil, then log.fatal error. Again, this is not the best way, but it's okay for us. Okay, and we also need to close the file. File.close. Yeah, so we can close the file if there is no error in the end. And then we use the scanner, create a buffered reader. Okay, and we scan it line by line. Oh, and this is how we read with custom buffer size. Read in chunks for binary data. So like there are many ways to read this, but what we want is we want a new scanner. buffio.new scanner, and we have this file. Since file already implements the IO reader trait, because this takes io.reader, so file already implements that. So io.reader is anything that implements the .read method, which is already implemented for file. I think we will go ahead with this one. I think, yeah, so they're saying that buffio scanner is the most efficient, so let's go ahead with that one. So we are reading it line by line and we are printing the line. If there is some error, we just log.fatal. I think panic is better for our use case because yeah, because this is something that shouldn't occur. So we are just enforcing that constraint that the error shouldn't be there, because this is a very small program not used in production and for our local use case. So I'll just do go run main.go, and cool, it reads the file, so perfect. And I'll I'll just come back in a moment. Okay. Yeah. So this is it. Okay. Yeah. So it's working fine. I'll just. Okay. I'll just confirm that. Okay. Cool. Yeah. So we are reading the file here, and now what are we supposed to do then? Yeah. So now we have this grid. Now we need to store this grid in a map. So basically we need an array of strings. Uh, okay, so we are just storing this array. So we are just storing this grid, and let's make our solve function, which takes the grid and gives us the number of rows that can be accessed. So I'll call it accessed, or interesting. Let's call it interesting roles. So we just need to return interesting. So interesting is those roles that can be accessed using forklift. Okay, so now what we need to do is we need to just iterate over this grid. So for I equals, or for j equals 0, j less than length of grid j plus plus, which is the height of the grid. So height of the grid is um, uh, yeah, height is simply the length of this array, and width is, again, this is not the correct way because this can panic. Grid can have, like, so it cannot, like, it can be an empty string and that will panic, but we are assuming that we don't have an empty string here. So I is equal to 0, I less than width I plus plus. Now we are at position so the character that we are accessing is actually grid I j, or is it ji? Actually it's ji. Yeah, because j is the length of this thing, or I'll just like call it ij for simplicity, like for readability purpose. So it's height cross width. So height is marked by I, and this is j, so it's ij. Awesome. So this is the character that we are referring to, and we need to make sure whether we need to know whether this is the interesting role or not. So now what I can do is I can just offset I offset x or x equals -1, x less than equal to 1, x plus plus for y. So we are just checking all the adjacent items surrounding this paper roll that we are accessing. So if c equals so if it is an empty so if we don't have any paper roll there, and if it's just an empty position, we just continue, so there's no point in accessing that. Else it is like a paper roll, and we just need to check if that paper roll is interesting or not. So now we need to access all the positions surrounding that paper roll. If I plus x, so if x equals 0 and y equals 0, then continue, because there's no point, like we can avoid the paper roll itself. And what we can do is then yeah, also if I plus x greater than 0 and I plus x less than height, and j plus y greater than 0 and j plus y less than width. So this is the only valid, so this is a valid position. And so what we can do is, if grid I plus x j plus y equals paper roll, so if it is a paper roll, then we just increase the count, and we should check if count less than 4, like if there are less than 4 paper rolls, then this is an interesting roll. Yeah, I think this is the solution. Just looping through all the adjacent list for all the paper rolls that we have, like for all the position. So we just need to print this, solve grid, and we get 13, which is correct for this case. Let's get our input then. It's a very large input, and 1560 is the answer. I think it should be correct. Yeah, so that's the right answer, and we can go on to solve part 2. Now the elves just need help accessing as much of the paper as they can. Once a roll of paper can be accessed by forklift, it can be removed. Once a roll of paper is removed, the forklifts might be able to access more rolls. Okay, so if this is a paper, we just remove that paper, and now we go on to do another iteration, and we remove the papers in the second iteration. After that, we go on to do the third iteration, fourth iteration, fifth iteration. So we continue to do that until there's no paper left that can be removed. So we can see that we have this cluster of papers centralized in the middle that cannot be removed. Like for any paper, like for this one, we have like 4 paper surrounding it, so we can't remove this. Similarly, this also has like 1 2 3 4 5 6 7 paper rolls surrounding it, so this can't be removed, and so on. So therefore we just need to do what we did again and again. So yeah. uh, so how can we solve this? So obviously we will need to keep on iterating, and I don't think that the length is too large. uh, so let's say that the like this is the height, this is the width, and obviously uh, if n is the height and width, so n square is the complexity for one iteration. And what's the worst case that we can do? Like, let's say that in the worst case we remove all the paper and each paper is removed in a single iteration. So in this iteration, let's say that we remove only this paper, then we go ahead and continue with the iteration again. Then in the second iteration we remove the second paper, third paper, and that way we just keep on removing all the n square papers. So n square is the complexity of one iteration, and the number of rows that we end up removing in the worst case is also n square. So the complexity would be n to the power 4. That is the complexity that we are looking at. And for that, obviously, fmt.println length or height and width. So length of grid and length of grid 0. So if we can just see the lengths, so it's 137. So I can just assume it as, for example, let's say like 100 of the order of 100, or let's say that it is 200 into 200 into 200 into 200, which is very large. Which is very large. So obviously if we are just iterating over this one by one, we have no option but to continue this process. What we can do is we can keep the positions of all the paper with us. Clearly, like, if clearly we are not removing only one paper in the iteration, but if we just look at the amortized complexity, if there are n square paper, then if n square is the number of iteration that we are doing, and we end up removing x paper, so the complexity is actually n square x. Obviously the proof is that, so we can just go ahead and implement this algorithm, but I don't think like the complexity would be too much, because if it is a very dense matrix, then we cannot remove the major set of paper. And okay, let's just go ahead and implement this. I'm not sure if I'm like thinking about this complexity thing right. So I'll also store this height and width, which is simply the length of the grid and the length of the very first row. And let's make an array called removed, which is nothing but an array of boolean of length height, and for I equals 0, I less than height, I plus plus, So we have just initiated a boolean array which is simply a grid, and um, so it is false by default. So if we remove a paper, we can mark that position as true. So now grid will take in the boolean. So solve 2 is part 2 removed. Yeah, so we do this thing again. Maybe it's um, better to be better to implement this as part of a function, so we don't keep on repeating ourselves. So, but for now, I'll just copy paste this. So the additional thing that we are doing here is actually we can implement. Yeah, I think just like yesterday we had this one function to implement everything. We can just implement this as part of this function only. Mm. So this is part 1 where we don't require the boolean, like this removed array, but for part 2 we will require this. To removed. Actually what we can do is, so total is 0. So let's say that n is the number of papers that were removed in this iteration. So if n is equal to 0, if we weren't able to remove any paper in this iteration, we know that in the subsequent iteration we won't be able to remove anything else. So we can simply break from here, and if we removed anything, then we just add it to total. Now here what we are supposed to do is that if count is less than 4, then this is interesting, and if removed is not equal to nil, then removed I j is equal to true. So I'll also pass removed here because I don't want to do this check. I want to avoid this check, and I know if removed and I think we can also do one more thing. We can yeah, so we can I think we can modify the array in place, so we don't even need this removed thing. So we can just mark that paper as interesting and try to and simply just remove it. So grid ij So this whole row is actually grid I, and row j equals this, and grid I becomes row. We cannot assign to row j. Can't we assign to a string? Ah, how to assign? How do we assign to a string? I have not run into this problem before. How do we assign to a string in Golang? Oh, I mean, how do we? Okay. Okay, I know how we can do this. So we can just convert this to bytes, or we can convert this to a byte array. I think this works. So we converted it to a byte array, and then we changed it to this, and now we will just assign it back as a string, and we don't even need to worry about this removed variable, and we can just return the interesting. So what we are doing is we are modifying the grid in place, and we use this hack to do it. We converted the string array into a byte array, and then we modified the byte in place, and we assigned back the string to the grid, to that particular row. Okay, now if I just run this, so part 1 is 3059, and part 2 is this, which is I think wrong. So part 1 was 1560. So okay, because we are modifying the string in place, instead of this, let's make it as x, and so we don't need this removed, we don't need this. And what there's also a function that we can write, print grid. Okay, and this goes for an infinite loop, which let's skip part 2 for now. Oh, if this is equal to this or c equals x, then move on. We don't have to worry about it. And still it's giving us the wrong answer, which it should give us 13. Grid I, we are accessing that. Then row J. Okay, so we cannot, so this is wrong. We cannot do, we cannot just remove that thing. So we cannot just remove that paper roll in the same iteration, because when we do this, then it affects the ability for us to remove other paper. So essentially we are removing more paper, because what we are doing is we are modifying it in place, which is correct, but we are modifying it in the same iteration. And if we do that, then the other paper rolls which weren't supposed to be removed in this iteration are getting removed, because the adjacent paper roll that we went through has already been removed. And because of that, we are like, when we are going to one paper roll which is like, for example, below this, it will see one less paper roll, so we are also removing that, which is incorrect. So what we can do is we can just keep a track of all the positions. So let's make a struct. And we can have an array of positions. So now we have this array of position, which is, can we just do it in line? Yeah, I think this is more readable, so we should focus on the readability. So now we have this array of position, and if it is an interesting paper, we can remove this. We can remove this, and this is something that we don't have to worry about now. So once it is done, so just before returning this, we can just iterate over all the positions, and we can mark grid ij equals x, or we can even mark it as that dot thing, but that's okay, we don't have to. Oh, okay, now we have to do that conversion. So again, row is equal to grid position dot x, row position dot y equals, and this is a byte array. So we can just convert this to a byte array initially only, so we don't have to worry about these conversion and stuff later on. Yeah, I think this will work. We can also solve it for part 2. copies the content of source into destination until either destination has been filled. So I'm just trying this function, destination source grid copy grid. Okay, we can't do that. So I just want to copy this thing here. Okay, for each row in range of grid copy equals append grid copy row. I think row copy, I think this should work. I think the other should also work, but because it's a local copy only, but because we don't want to modify the original grid for part 2. So part 1 is 13, part 2 is 43. Let's say, let's see that what is the answer here. Yeah, it's 43 only. Okay, and we don't want to print the grid again because that is useless. So part 1 is 1560, part 2 is 9609. 1560 was correct, so 9609 should be our answer. Just also paste the screenshot here, remove the useless parts. I can use this carbon thing. I want to use something good enough, which is okay. This is okay. And remove this function. Okay, just carbon.png. Okay. So this is done, and let's try to see if we can also solve this in Rust. So I'll just I'll just import over the same function. So this is our original function, and I'll just go to ChatGPT and ask to import this in Rust, and then we can look and like observe what are the changes that go into writing this in idiomatic Rust, because we can obviously use the same logic, but that is not something we should do. We can look at how Rust handles things. Yeah, and it's pretty cool. So just to explain the solution, so we have this main function. I think this is much better to see. So we are opening the file using file open, which we have imported from the standard library, and we are using this dot expect because it is kind of doing an unwrap, because we know that this shouldn't result in an error, but we should gracefully handle the error if this is a production thing. Then we are using buffered reader, which takes in the file. So buffered reader actually uh, takes R, which implements the read trait, but may change in the future. Okay, the default is currently 8 KB. So read is a trait which implements the read method, which takes a mutable reference to self and a buffer and writes this self to buffer, I guess. Okay. So it takes in something that implements the read trait. So file clearly implements that trait. This is also something that is similar in Golang, where we have this io.reader interface that must be implemented, which is implemented by file strings and other uh, implementations that we have there. So now we are reading it into a grid, which is a vector of vector u8. So we are just reading the bytes. So byte is nothing but a 8-bit um, 8-bit thing. So like it's a 8-bit integer. Uh, so we are just reading it. We are reading it, and so it is reader dot lines. So reader implements dot lines method and dot map. So for each line we are converting it into bytes, and then we are collecting it into this vector. So this into bytes gives us a vector of u8, and collect gives us the vector of t, whatever this t is. In this case it's vector of u8. Now we are also using this grid copy, which is grid dot iter dot map, and we are just cloning the row here and collecting. This is pretty neat. And we are using the solve function to and pass in the copy of the grid. This is for the first part, and for the second part we are doing a similar stuff. So now we just have to worry about how we implement this solve function. So this is pretty interesting. So now it has like also created the struct position that we had for our Go um, implementation, and for all the positions, um, so it is grid dot length width is grid 0 dot length. So now it's doing the same thing that we did in Go, which is pretty cool. New I, new j, yeah, new j as usize. If it is byte of this, then count plus 1, and then push everything to, like if count is less than 4, then interesting, and also push the position and mark the position as x or dot, whatever. And yeah, so this is pretty interesting actually. I love how it's reading the input and output such a clean way as compared to our Go implementation, and this is pretty cool. And it's also suggesting that we can. Oh, we don't have this input file. Mm. Yeah, so it gave us the same output, and it also suggested an optimization called 2vec, which gives us something, like which gives us a vector of t where T implements the clone trait. Here S and X can be modified independently. So yeah, this is pretty awesome. And I think, uh, so yeah, this is something pretty interesting. T is something that can be cloned, but here T is actually vector of U8 itself. Now, now if we just think about it, if vector of T implements where T is clone, then obviously, um, if T is also a vector of, let's say, U, then obviously U is also cloned. I think this is pretty interesting way to do things. So I'll just write this and see what Claude has to say about this. Mm, you're absolutely right. This implements clone using .2vec. So it works because it works on a slice of vector U8. It clones each element. Since vector U8 implements the clone, it performs a deep copy. So this is a pretty interesting thing in Rust, that if there is some type T which has this copy trait and it itself has something like, for example, U which has the copy trait again, Rust will automatically take care of performing this deep copy, which is pretty cool. So each inner vector U8 gets its own separate allocation. So if we weren't doing some straight copy but doing a transformation, then we would need this iter dot map thing, but we don't need it here. So that's cool. And so suggesting some quick. That is not something very interesting. Okay, so this is the solution in Rust. We did not like implement it ourselves, but just ported our Go solution to Rust. So yeah, this is it for today. We were able to solve day 4 also, like both the parts. So not a problem. I think we can continue, and I'll see you in the next stream. And let's see like how long can we keep going over this, because I'm pretty sure like things will get tougher with time, but let's see. So thank you.